through them for any further comments, and then open up the panel for questions. Dr. Morrison.
Thank you, Edna, and welcome everyone. When I was young, a long time ago, and starting to study astronomy, asteroids were called the vermin of the skies because they would make ugly streaks across otherwise beautiful deep sky photographs of galaxies and nebulae. And so no astronomer wanted their picture to be ruined by this ugly little rock passing in front. Our attitude has changed a great deal. What we are going to focus on here is near-Earth asteroids, the small ones whose orbits cross the orbit of the Earth, the orbit of Mars, and who share our part of space. Some people have described this as that Earth is living in a cosmic shooting gallery, because these little guys, anywhere from several kilometers across down to just meters, will eventually either be ejected from the solar system gravitationally or crash into a planet, and the most likely planet is Earth. So when we look at any near-Earth asteroid, there's something like a 20% chance its ultimate fate will be collision with our planet. That interests us, especially if they're big enough to do serious damage. But there are many reasons that people now are increasingly interested in near-Earth asteroids. The first is simply that they're there. They are a significant part of our solar system, of our cosmic neighborhood. They are made of the same materials that were the building blocks of the Earth and other planets. So we can learn a lot about the origin and history of the solar system by looking at these small objects, including sending spacecraft for a really close look. They are a significant danger. Now, I don't want to exaggerate that. People sometimes used to call me Dr. Doom, and I've decided that wasn't a compliment. But the fact is that many of them will eventually collide with the Earth. And if you consider the larger ones, the ones more than 1 or 2 kilometers in diameter, they actually are the worst thing that we think could happen to our planet. They exceed the damage that could be done by the largest earthquakes or volcanic eruptions or hurricanes. The only thing that can even come close is the sort of super eruption of a volcano like Yellowstone that happens every million years or so. They also, potentially, could be valuable space resources. If we ever have a robust space economy and need materials in space, then there's the asteroids with everything, water, carbon, iron, almost anything you can imagine, relatively easy to grab. Whether that would ever be economically viable to pick up an asteroid and bring it to the Earth is questionable, but if you can use them in space and not have to haul things up through the deep energy hole that the Earth is in, then that could be important. We're not there yet, but someday we may well be. And then finally, we are now seriously considering sending humans to visit asteroids. President Obama, a little more than 2 years ago, stated as his space goal for human spaceflight, for manned spaceflight, to visit a near-Earth asteroid by 2025. How did this come about? Well, it partly is because the alternative of the moon, ironically, seems too expensive to get to. Because to land humans on the moon, you have to have a lander, you have to have a rover, a habitat, you have to have a return vehicle to come to Earth, and that seemed to exceed the budgets that NASA could expect. So asteroids are easier. You don't have to land, you don't have to have a rover. You go out there and visit and come back. And more to the point, they expand the envelope. We've been to the moon, and I hope we'll go back. But to go to the near-Earth asteroids means truly going into deep space, going to the point where the Earth and moon are just stars in the sky. And therefore, it is a stepping stone on the goal of human visits to Mars. I like that. They're rocks, and they're stepping stones to our future in space.
Thank you. So my name is Franck Marchis. I'm a researcher here. I've been studying asteroids for like 15 years. So I'm not that young.
Pull your mic a little closer.
Okay. So what I wanted to say is that what I basically do in my research is to study the internal structure of asteroids. How we do that, well, we cannot go over there and take a sample yet, but we search for binaries. We search for asteroids which possess a moon. So imagine that this is an asteroid and we have another asteroid here. They come close to each other, they enter in each other's gravitational field, and they start rotating. And what happens is that by studying this motion, the rotation, we can infer the bulk density, the composition of the asteroid. And in fact, that's the only way we can do that, except if we send a spacecraft over there. But sending a spacecraft to an asteroid is extremely expensive. So us, with our tiny 8-meter class telescope or our radar observation, we basically search for this asteroid with moon, and we derive the density. Something happened over the past 4 years, and that's an interesting development in the world of asteroids, that we now know that asteroids are not inert body, they're not dead body. They in fact evolve in a way that they give birth to other asteroids. They split in two, they shade materials, they change their shape as well due to the rotation, for instance, especially the small one, the NEA asteroid, the near asteroid that you mentioned, Dave. So now we know that 10 to 15% of asteroids are binaries, so we start having a better understanding of their composition. Recently we found out that most of the asteroids are in fact extremely porous. We don't know if they're made of fluffy material all around, or they have a core, very dense core, and fluffy around. And that's important because if you want to start mining an asteroid, you definitely need to know the composition of this asteroid. The future is bright for our field. It's bright because minor bodies are in fact the priority for most of the space agencies. Let's talk about the main one. NASA selected recently a New Frontier mission, one of these mid-class missions. It's called OSIRIS-REx, which is going to fly to a near-Earth asteroid called 1999 RQ-36, but we're going to change the name, don't worry. And this mission is going to go over there, fly around this asteroid, take a sample, and bring it back to Earth. The Japanese agency, the JAXA agency, selected recently the Hayabusa 2 mission, which is going to do basically the same in 2018, 2019. It's going to fly to any asteroid and also bring back a sample. And finally, the European also wants to have their space mission to an asteroid, but they're European, so they're ambitious. So the idea is to go not to one asteroid, but to go to a binary system. That's the mission called Marco Polo R, and they are going to visit the two components of the system, the two asteroids orbiting around each other, and grab a sample of one of them and bring it back to Earth. So this is the first step, as you say, the first step to a human exploration, and it's also a first step to asteroid mining. Because as I say, what we really want to know now is how we form this asteroid, their composition, and we want to be able to select the asteroid which is going to be interesting for us, for the next project, for our next adventure, and the next step in exploration, in exploring the solar system. Thank you.
My name is Peteryanis. I like to make astronomy out of meteors and fireballs. So I was very interested when a small asteroid was spotted in 2008 that was actually calculated to be on an impact course to Earth. So far, that's still the only asteroid discovered in space so far that actually hit us. And it crashed in north of Sudan. I teamed up with students and staff members from the University of Khartoum, led by Maurice Shaddad. And we went out and we found actually pieces of it. And what struck me from that experience was that the pieces we were picking up in the desert were all different. Most of these pieces we were picking up were black and sort of scruffy looking. They were urealites, which is a rare type of a meteorite. But 20 to 30% of what was in the desert was ancetite chondrites, in itself a rare class, various ordinary chondrites, some ordinary chondrites that nobody had ever seen before. So this thing was big. This was a 4-meter size asteroid that came crashing in. As far as asteroids hitting us, that's big. And that sort of brings home the idea that if you have an asteroid that big, you're really talking about a small world. This thing is not just a solid block of one thing. It is a really, at least it can be, in this case it was, a really diverse, interesting object, complicated. And if you talk about a thing coming in at 4 meters in size, 4 meters is sort of your car, okay? That's human scale. That's really sort of the type of asteroid you would like to hover around and pick rocks, choose and pick rocks from. So it's a really neat sort of object to go to as a human mission. And I think that if people are looking at what type of objects in the future are going to be visited, what type of near-Earth objects, they are not that big. The typical sizes that typical candidates that people are identifying are sort of between 10 meters and 50 meters. And that is because if they are much bigger, we simply do not know asteroids that are in convenient orbits to go to. So it's the small objects that seem to be good targets for human missions. So that means that if you have a 4-meter size object, you're really looking at one of these things that one day we might got to go and see in detail. So when 2 months ago we had a big boom over the Sierra Nevada mountains, and it scattered meteorites in gold country at a site called Sutter's Mill. Yes, that is the very site where gold was first discovered in California. That was very exciting to me, because here was an asteroid maybe 3 meters or so in size, the same sort of size that matters. And so we've since approached this fall at Sutter's Mill very much in the same way as we did the one in Sudan, where each piece that you pick up could be something unique. And each meteorite is not the same. You could really be looking at different parts of a small world. So yeah, these really big fireballs, these really big meteorites, these small asteroids that are hitting us once in a while, those are really, really interesting to me, and may tell us more about what sort of things people would ultimately be visiting and exploring.
Thank you, Peter. Good morning, everybody. I'm Tom Jones. I'm interested in all kinds of the dimensions of asteroids that we've talked about already this morning. I'm, of course, interested in human exploration of asteroids. As far as I got was about 220 miles into space, and I would surely like to see other human explorers get to a few million miles away to visit these small neighbors of ours. Those missions might take 6 months round trip, and of course, you know, NASA's working on the technical and policy challenges of accomplishing a near-Earth asteroid mission. There are several good reasons in my mind that they should be in the destination set for human explorers, as well as the moon. The machines that you build to go to the moon have the same rocket energy needed to go to nearby asteroids. So the asteroids fall into your lap if you're designing machines that can go to the moon, and vice versa. If you design an asteroid transportation system, all you need to do is add a lander and you'll probably have the capability to go to the moon's surface. And they're complementary destinations. So asteroids give us, of course, great science dating back to the origins of the solar system. By visiting a few of these objects, we'll really fill out what our meteorite collections have tried to tell us so far. We also want to go to the asteroids for their information on operations, on getting our stepping stones to deep space, the Martian moons, the Martian surface eventually. It's a tremendously valuable operational experience to leave Earth's orbit and get out into deep space on shorter missions without the huge risk of going to Mars in one big step. Also, we'd like to go to asteroids to learn about their interior structure and physical properties so we can do a better job of planetary defense. Robots can help us there. Humans will return a tremendous amount of civil engineering information about these objects. And finally, the resource potential is very exciting to me. Astronauts, I envision them setting up a series of boxes on the surface of an asteroid that will process asteroidal material and produce a variety of projects. The human crew should be bringing back test tubes of asteroidal water and other volatile elements and metals and so forth as test prospecting ventures on asteroids, and then turn all that information over to commercial mining concerns. I'm working with the Planetary Defence folks at the Association of Space Explorers, all the cosmonauts and astronauts around the world, at the United Nations to try to come up with a decision-making process by which the countries of the world can decide how to prevent a future rogue asteroid from striking the Earth. That's a very slow and tedious talking process at the UN, but it eventually might help us collaborate on deciding how to technically divert an asteroid, and that's an ongoing exercise I'm involved in, just as important as the technical or technology dimension. That planetary defense mission is always in the front pages these days. We've had the Sutter's Mill meteorite just yesterday. A 1 kilometer asteroid flew by at 20 lunar distances or so, examined by the Arecibo radar, and we found out that it was twice as big as we originally thought it was at discovery on June 10th, because we just didn't have a good estimate from its brightness as to how big it was. The radar gave us a very precise measurement, and fortunately it's not going to hit us in the next 750 years or so. So we're always discovering these new asteroids, and of course some of them are going to be potentially hazardous. And it strikes me that we need to increase our search capabilities to find the smaller asteroids that still have an unknown potential for striking us. And if you think about the event that caused the Tunguska explosion back in 1908, a 3 to 5 megaton explosion, the asteroid that caused that is 30 or 40 meters in diameter. Much below that, the atmosphere prevents them from striking the surface. But if they're a little bit bigger, they'll make it all the way to the ground. And there are about 500,000 objects like the asteroid that caused the Tunguska event, and we know less than 1% of that population. So we need to get out into space with a small telescope, very affordable, like the B612 Foundation is proposing, and NASA can collaborate on, and find the smaller populations of asteroids that can still do in an Earthbound terrestrial city. I want to share with you just very briefly the results of a very interesting study by the Keck Institute for Space Studies that was done this past year about nabbing a nearby asteroid and bringing it back to Earth-Moon space. And I was on the study team. We just talked about it this past week and this past month in Washington at the Global Space Exploration Conference. Here the idea is not to send humans on a 6-month or more round trip to an asteroid, but you send a robot, solar-powered spacecraft, ion engines, out to grab a boulder about the size of 7 meters across. You know, this would fill the half of the front end of this room. And a robotic spacecraft for over a 10-year mission costing about $2.5 billion, about the cost of a Mars rover, could go out and snare a 7-meter asteroid. It weighs about 500 tons, bring it back to a high orbit around the moon or to the L2 Lagrange point beyond the moon, and make it accessible to robot and human explorers in Earth-Moon space, thereby sort of jump-starting the whole process of astronauts going to nearby asteroids. You bring the asteroid to the explorers so that they can take little steps into the risk environment that they'll encounter when they go out into true deep space. So it's very exciting that we can see a very feasible, affordable mission over about 10 years, and we can get this asteroid into near Earth Moon space, near Earth and Moon space, and turn it over to commercial concerns for prospecting and mining, turn it over to the scientists with hundreds of kilograms of samples being brought back by Orion-carried explorers in the Earth-Moon system. That's a very exciting feasibility study that I think will get some more attention from NASA. And lastly, let me talk about this commercial mining idea. As you know, in April, the company Planetary Resources announced that they wanted to do asteroid mining. They're backed by a lot of Silicon Valley investors, and they're being very cagey about their plans. I just help them on the science side of things. The plan apparently is to develop in small steps increasingly more capable spacecraft that can eventually prospect and get up close to asteroids and return samples of what they're made of that might be commercially valuable. The biggest product, I think, would be water. There's not a big market yet for space resources, but the most obvious thing to extract from a carbonaceous type asteroid would be water. That makes up about 10 or 20% of those bodies. And at $20,000 a kilo or a liter, you're going to find that the space agencies of the world might be able to buy that product from you in the next 10 to 20 years to help lower the cost of overall exploration. And so, for example, that 7-meter, 500-ton asteroid that we talked about bringing back robotically, that might have something like 100 tons of water in that body available for extraction using solar energy and then selling it to local space agencies. I think that's the near-term bright prospect for asteroid mining, just as the water resources on the moon are very attractive if you're going to be doing surface activity on the moon. So let me wrap it up by just saying I think that asteroids are a multidimensional set of objects that have benefits across the board in science, in helping us defend the Earth, and in opening up our inner solar system for future exploration by lowering the cost and providing experiential stepping stones to Mars one day. And I'll be, after this panel, right out in the book signing area by the store, signing my books about future space exploration, including asteroids as a dimension of that. So I look forward to talking to you all. Edna?
Great, thank you very much. I'd like to now move on to questions, but I'm going to offer the panelists the first opportunity to remark or if they have any questions for each other.
Thanks, Edna. I'd like to just quickly comment on two what-ifs that may get some of our brain cells operating. First is, what if we discover an asteroid on a collision course with Earth? First of all, of course, we have to do surveys in order to find them. They're not going to just advertise themselves with a red blinking light. But we really have studied ways that we could deflect an asteroid, change its orbit slightly, assuming we had years of warning, so it misses. And it's the only natural hazard that we could completely avoid by using technology. You couldn't stop an earthquake or a volcano, but you could stop an asteroid. Putting that another way, why are the dinosaurs not still with us? It's because they didn't have astronomy and they didn't have a space program. Those are the two things you need in order to protect yourself. The other addresses what Tom is talking about human visits to asteroids, and I must admit I'm a little perplexed in the first case as to what people would do when they got there that the robot couldn't do. Some people say, well, you know, a human is uniquely able to go and stand on the asteroid. Asteroids have so little gravity, nobody could stand on them. In fact, maneuvering around an asteroid is more like maneuvering around the space station in microgravity. But as someone mentioned, the difference is the space station has handholds. So I think we need to ask ourselves, in the long run, there's lots of neat things to do, mining and analysis and so forth. In the short term, what do you in the public, what would excite you about the first human flight to a near-Earth asteroid? What should they do? Should they plant a flag? Should they touch it? Should they operate rovers? What would make such an expedition worthwhile? We all think it's worthwhile because it's a stepping stone to bigger and better things later. But I'm still a little mystified as to what the astronaut will do on that first arrival.
Gentlemen, any comments, responses?
Oh, sure. I think it's wrong to focus strictly on asteroids as a destination for the United States human spaceflight program. I think that the right approach is to talk about getting the ability to go into deep space beyond the space station. That includes the moon. That includes, with those same vehicles, going to asteroids for 2 or 3 or 4 visits to build up experience, and then you go on to the moons of Mars, or you go on to develop an economy between the moon and the Earth. And I really think that we're never going to get to Mars, quite frankly, until we use human skills to industrialize Earth-Moon space. And that involves tapping the wealth of the asteroids. It means humans get involved in demonstrating processes that can then be turned over to commercial concerns to robotically extract asteroid resources. I agree with Dave that robots can do a great job of reconnoitering and landing on asteroids and prospecting them, but at the current pace, we're going to see 1 or 2 asteroid missions every 10 years with current budgets. So unless you've got a human program to go there, the results are going to come in so slowly that everybody's going to lose interest and wander away. So astronauts bring a rapid avalanche of results that will, I think, kickstart the entire resource extraction business or industry.
So Peter, do you want to go?
Oh, I disagree that going to an asteroid is not worthwhile the effort. I don't see robotic missions do what humans can. I'd be really exciting to see this little asteroid. I'd really excited to dig in and figure out what's below the rocks and below another rock and just sort of take it apart. This is really exploration. This is a new place to go.
I will just say that I think the choice, the reason for which we should think of going to an asteroid is because basically it's a short pace exploration program. If we want to go to Mars, it's going to take a long time, many years,
decades.
More than decades, more than the budget of NASA will sustain, and more than the interest of the people. So an asteroid is an easy place to go because it's on a short time scale. You can motivate an entire generation of young people, and when they become adult, they will basically see an astronaut on an asteroid. And that's, I think, this is the new lunar space program for the next generation.
Okay, I imagine some of you have some thoughts about flying rocks. And this nice gentleman will hand you a microphone. I ask that if you would like to ask a question, you make sure you get the microphone first, so first of all, everyone in the room can hear you. And secondly, the recording that is being made can capture your question. So who has a question about flying rocks? Here we go. A gentleman toward the back of the room.
I know you know me better than that. I'm no gentleman.
Oh, hi, John.
Okay, anyway, I wandered in a little bit late, but I wanted to, in the spirit of what Alan Stern was talking about last night in the commercialization of space, would it make any sense to turn this over to entrepreneurs to have a go at it and commercialize the exploitation of asteroids, or there's just no conceivable economic upside at this point?
I think Tom is probably in the best position to answer that. It would be wonderful if the commercial folks would feel motivated to go to an asteroid, but that's asking quite a lot from people whose main job is to meet profits on a quarterly basis.
Yeah, I think that what I heard from the Planetary Resources folks in April when they made their announcement was that they've got enough investment money behind them to orbit a small telescope to help in the search for asteroids. It's not an overall solution to finding hazardous asteroids or even good prospects for resource-rich asteroids. But it's a step into operating small, cheap spacecraft that can then go out later in other generations to deep space and then eventually get close to promising asteroid candidates. I think that their ambition is to, about 10 years from now, be up close and scratching an asteroid to bring back a test tube of water or some surface dirt that contains a rich metallic iron nickel content with a side helping of platinum group metals to assess the kind of materials they might find there. And I think they're going to sort of surprise themselves along the way with the challenges of how tough it is to build reliable, cheap spacecraft that are 10 times cheaper than current ones. So let's watch and see how their investors' patience develops over 10 years. And this is why I think it's very important for NASA to take a hand in reducing the risk of asteroid mining or asteroid prospecting. They should do some of the demo with human explorers, as I mentioned. I think this returning a small asteroid to Earth-Moon space is a great way to bring hundreds of tons of asteroidal material and bring it within range then of companies that can afford to get just out of Earth orbit, not take a 2 or 5 year trip out to an asteroid. So that's a way for NASA to put a resource nearby and then let all the international partners involved in the space station, for example, and then all the commercial companies have at dissecting 500 tons of rock. And that's a good 10 or 20 year project right there.
What I think NASA can and will do is buy data. That's the best way to team with the commercial products. If a commercial organization or anyone can put up a telescope and do a survey, NASA can pay for the data and pay enough to make it a worthwhile commercial activity.
Yeah, I just would like to add that my fear with all these private companies is that I'm not sure they will have the patience to wait for the scientific part to be done, because if you want to mine an asteroid, you really need to select the best candidate, especially for the first one. And to select the best candidate, you will have to watch a lot of them, to search for a lot of them. I mean, we know like 1,000 of them right now in NEA population. We need to at least survey millions of them. For this, we are building from the ground large telescope like LSST. They are going to be capable of observing the entire sky every 2 days. and finding the faintest moving target up to magnitude 24, which is basically the size of 140 meters. But this will take time. It will take 10 years.
2030.
Yeah.
Okay. Question? I saw a hand up down here someplace. Okay, he's rushing back to see Pascal Lee.
Want to ask a question? Amazing.
Aha, different person.
Hi. Sorry, English major question here. Warning, not a scientist. So 2 questions. Why is the Earth surface not covered in tons of asteroid craters while the moon is? Or is that just an illusion? And also, if other asteroids have hit the Earth hundreds of millions of years ago, wouldn't there be a lot of asteroids buried in the Earth's surface somewhere that we could mine?
Yeah, 2 interesting questions. Yes, the Earth has an awful lot of asteroidal material mixed into the crust, but it's been completely processed and absorbed into the Earth. I mean, the Earth's made of asteroids initially. So it becomes part of us and loses the mineral and the physical memory of where it came from. Same thing with cratering. When an asteroid hits, it explodes, it vaporizes. And so you're not going to find a lump of rock down there. You're just going to contribute to the Earth at the rate of about 100 tons a day.
And I will just add that, in fact, the water you're drinking is most likely water which is coming from asteroid in the outer main belt. We know that because we measured what we call the DH ratio, and the DH ratio of the water on Earth is similar to the DH ratio of water in the outer part of the main belt.
DH is deuterium dihydrogen.
Thank you.
And we don't see craters on the Earth. We've got 180 that we have found, but we don't see them in the density that the moon has because the Earth is a dynamic world with plate tectonics. The crust disappears into the mantle and gets recycled, so those craters get recycled and eroded away. But the moon is a great tape recorder for the bombardment process of the solar system. That's why we know that we're in a shooting gallery.
Next question. Aha, Pascal Lee now.
Hey, good morning. So first of all, I have a comment and a question. The comment is, well, I agree with every last person who spoke. The thing I would say about the motivation or the reason why we would even send humans to asteroids is that the public's attention and interest in human missions is really not measured by the quality or the amount of science that's returned by mission. That's just a simple fact. The public's interest is really driven by the fact that we're doing firsts that are exciting and are taking us to a goal that we deem to be of value. So missions like Apollo 7, Apollo 9, Apollo 8 were not particularly exciting inherently. We weren't going really anywhere, but they were major milestones towards this goal that everybody was on board with, or many people were, which was to land on the moon and come back.
And your question?
So the comment is, going to asteroids to me makes total sense as long as it's cast in this view of us going to Mars and visiting the moons of Mars as a first approach to Mars. The question is for Peter. Peter, how do you know that the other meteorites that you were picking up, above and beyond the Eurolites, were not from other falls? In other words, you're in a desert after all, you might have meteorites.
Yeah, we spend a lot of time researching that because that's the obvious thing you would expect. There were other meteorites there already, and we were just coming across that. The area was huge. It was 30 by 7 kilometers or so, which we were surveying. But the reality was that these were all fresh meteorites. They were completely unweathered. They had black fusion crusts, all sorts of different types. We had, among the small pieces and the big pieces, a lot of size sorting going on. We found the same diversity. So there was not that in one area you found enceitite chondrites, in another area you found something else. We measured cosmic ray isotopes, the ones generated when the meteorite is in space and which decay very rapidly once the meteorite is on the Earth. And we're actually able to show that even these non-Eurolites, these ornite chondrites and enceitite chondrites, were just recently fallen. And they came from a really big object, just like the Eurolites were. And so what are the chances of 2 really big objects falling in that same 30 by 7 kilometer area? So we had a lot of arguments to say, no, these were all part of 2008 TC3. 2008 TC3 was a really interesting quite extraordinary object, but maybe not that uncommon. It's just that we don't have studied in detail that many really big, from my perspective, really big asteroid impacts.
I just would like to add that NASA, JAXA, and ESA are spending millions of dollars to get a sample for an asteroid. And Peter could do it with just a trip to Sudan or just crossing half of California. So.
But with the students of Sudan from the University of Khartoum.
That's great. Okay, next question.
You talked about going to an asteroid and then bringing back a sample. Would there be an advantage to doing that as opposed to picking up parts that are meteorites from the Earth, in that that asteroid would not have gone through the atmosphere? So would there be a benefit to doing that?
It's mostly about making these links. We have all these asteroids in space, and we have many different asteroid classes. We can see they look a little bit different. They have slightly different colors. They're darker and lighter and so on. Yeah. And we have about 40,000 meteorites in our collections. But we really don't know how these two are related. And so the idea that you sort of try and understand which meteorite that gives you all this geologic information corresponds to what asteroid class, that's really what motivates this.
And I would like to add that what motivates us is also to know the structure of the asteroids. If you go on an asteroid, think about an asteroid has zero gravity almost. So the way the material is aggregated is different. So we don't know if, for instance, the material is extremely fluffy, like if you put your hand, we go deep into it for at least 20 centimeters, or if it's a very compact rock. And that's important because that changes the property of an asteroid, the way it's reacting also due to the solar wind, the interaction with the sun, and also we have an impact if we want to mine an asteroid, because the technology will be extremely different in this case.
I actually am very sympathetic to your question. You know, the cheapest way to get samples from other places is to go down to the Antarctic and pick up rocks. But there really is an advantage in knowing where it comes from. We now, at the time of Apollo, we didn't know there were any moon rocks on the Earth that came as meteorites, and now we do. But we still greatly value the rocks that were picked up on the surface of the moon because we know where they came from, we know the context in which they exist, they've been put and sealed and kept away from contamination, whereas the meteorite from the moon that fell in the Antarctic has been exposed to centuries, millennia of water and ice in our atmosphere, which does degrade them significantly.
And can I add something? The Dawn mission, it's a mission which is orbiting around Vesta, identified the source of what we call the HED meteorites, which is a very specific kind of meteorite we have been observing on Earth and also on other planets. And basically, after visiting Vesta, Dawn has been capable to probe, to nail down where this kind of meteorites was coming from the south pole of Vesta. So that's the interest of exploring the body being close, because you see structures and you see that is not homogeneous, for instance.
Okay, Andy.
It's on? Good. So I think the panel has been way too peaceful, and I want to get back to something more scary. So I understand that when we observe asteroids that are near-Earth asteroids, there's a wide range of sizes. The really smallest ones burn up in our atmosphere. The really big ones have been cataloged by Spacewatch and other good projects. But what about the medium ones? So my question is sort of two-part. What do we know any more about the smaller Earth-crossing asteroids? How many there are? How many of them we've found? And if we do find one that is sort of that's got our name on it or our number on it, are there things we can do with smaller asteroids to deflect them or destroy them or to do something about them?
Well, Andy, it's a big question as to what you mean by small. Some people here think a 4 meter asteroid is big. Some think it's small. But we have discovered a lot. When you and I first wrote our textbooks, there were only a handful of near-Earth asteroids known. Now there are more than 9,000, and a lot of those are small ones. And fortunately, none of them that we have found so far is on a collision course. But if we found one on a collision course, and if we had sufficient warning, then we could deflect it in the simplest possible way by simply running a spacecraft into it and transferring that momentum and changing its orbit ever so slightly. We don't need to nuke it. We don't need to put on some sort of fancy pusher spacecraft. It's just simple Newtonian mechanics. Here's the asteroid, bang something into it, and you shift its orbit so it would miss the Earth completely. So objects like Tunguska, objects in the few tens of meters, up to a couple of 100 meters size, we have the technology to deflect them. All we need is surveys to find more of them, with the hopes that eventually we'll find the next impactor before it impacts and can do something about it.
I'd add that we're not spending enough to buy asteroid insurance today. The problem that Dave has cited is that we don't know about the small end of the asteroid population. We're not finding out about them rapidly enough. As we've heard, it's going to take about 10 to 20 years for the ground-based telescopes to start filling out the catalog down to about 140 meters, which is where we retire about another 90% of the risk that exists from asteroids today. So, the top of the asteroid risk table right now is 2011 AG5, which is about a 140-meter object. It has a 1 in 500 chance of hitting us in 2040. And NASA had a workshop a few weeks ago that I attended. That particular object is a poster child for all the thousands of undiscovered asteroids that might have higher odds than that of striking us. So in order to get to those asteroids and discover them more quickly, find them early so that we can use our technology to deflect them, NASA has to spend more than the $20 million a year that they're spending now on asteroid searches. And the number that the panel that I served on came up with a couple of years ago and recommended to the NASA administrator is that he should spend about 1/60th of his budget annually, 1/60th, which is about $250 million or so, on asteroid searches and technology for deflection for about 10 years until we get the catalog filled out by flying a space telescope, and we do a demonstration mission to a nearby asteroid to show that we can knock it off course in the way that Dave described. So we've got to buy that insurance, and that can be an international bargain for all of our space partners to help us pay for that cost, but it's a public safety issue that we ought to be investing more in.
I have a question to ask. I understand that the number of people who work full-time on this is less than the staff of your local McDonald's restaurant. Is that true, or are there more people working on asteroids now in terms of being concerned about the near-Earth asteroids and finding them and working on deflecting them?
Well, coming back from the ACM conference, which is the major conference in this field, and there was only 900 scientists, so it was a very small conference compared to any other conference, such as in cosmology. I'm comparing astronomy with planetary science with small solar system bodies. So in fact, small solar system body astronomers are a very small community.
If Edna is as I think, focusing just on those scientists and engineers who are working on discovering the near-Earth asteroids and thinking about the deflection, it's gone up from 1 shift at a McDonald's to about 3. But there are certainly more people in this room now than the full-time equivalent number of scientists and engineers who are actively working on planetary defense. Not the science, there are more scientists, but on the planetary defense. It's a very thin line of people standing between you and Armageddon, if I can use that awful word.
Inside the water of an asteroid, and then when the asteroid crashed into Earth, brought life to Earth?
Could life have started inside of an asteroid, and when the asteroid came to Earth, could that have started life on Earth? This is a panspermia type of question, I think. Anybody want to comment?
That's for you.
Looking at me.
That's for you, because you're the meteor guy.
I'm the meteor guy. Okay, so a lot of people like this idea, that life started somewhere else, and that comets or asteroids brought it to the Earth. Because we see lots of asteroids from space fall on the Earth, and so we think that that's an interesting idea. There's been a lot of studies done on whether life, if you really dry it out, and if it's really the right sort of life, whether that can survive space travel in an asteroid or in a comet. And the answer is yes. To a certain extent, it can. Now the question is this possible, or is this a reasonable idea or an appealing idea? And the problem with the idea is that if you have it come in from somewhere else, it still has to form somewhere else. And you have to come up with an idea on how life started on some other planet, or some other place in the universe. And so you're really just pushing away the ultimate question, as in how did life originate? And so as long as there's no real evidence for life being in meteorites, life unlike what we have on Earth perhaps now, because we certainly know life on Earth has evolved from whatever came in early. So as long as there's no life found in meteorites or in comet particles we're collecting, then the idea, it's a nice idea, but it's not helping us understand necessarily how life originated.
Thank you, Peter. Next question.
If asteroids form from the same protoplanetary disk, why would one be radically different from another? Why aren't they more or less homogeneous? What are some of the factors that would make for differences among them?
Yeah, go, Frank.
Well, the protoplanetary disk, which is the place where form all the planetesimals, so the asteroids, was not homogeneous. And also the temperature in the protoplanetary disk has changed drastically, because close to the protostar, which is the path of our sun, the temperature was high, so there was no volatile element, for instance. And the further away you go into the protoplanetary disk, the more icy element you find. So that's one of the reasons we think that trans-Neptunian objects, this large body, are made of ice and rocks, because they're far away from us, beyond the orbit of Neptune. And the closer you come, the more mafic, so more rocky elements you will find for the asteroids. Then we also know now there is a mixture, and we don't really know the origin of this mixture. We don't know how this mixture happened, and this has been shown by the recent observation of asteroid that you did, but also some of the Genesis result, the famous mission which opened a sail nearby a comet.
Thanks. Next question.
Okay, this is working. I wanted to get back to the planetary defense question. And I guess, Tom, you had said that you were recently doing a lot of work trying to, basically helping the nations of the world decide how they were going to respond. And I'm wondering, I guess, if you can expand on that a little bit. How much debate is there really about across nations about what to do if we find the asteroid with our name on it?
Well, the good news is that at the United Nations Committee on the Peaceful Uses of Outer Space, which meets a couple of times a year in Vienna, Austria, there is a standing panel underneath that committee that deals with decision-making for hazardous asteroids, recognizing that this is a natural disaster, that's a global problem, and that we can work together to pool our resources and ideas and experience to prevent it from happening. So that's good. But of course, it's at the United Nations where things happen very slowly. And we can all think of examples of how the United Nations takes forever to not do anything. But there are precedents at the UN dealing with space debris, dealing with natural disasters and supplying relief aid around the world after a catastrophe. So there is precedent for the UN providing a mechanism for coming together and solving a joint problem. And why it's a joint problem? Well, because asteroid impacts occur all over the world. And if one is coming to hit Santa Clara, the technology involved in knocking it off that trajectory and making it miss its appointment with Earth will involve changing the impact point from Santa Clara through San Francisco, through Tokyo, and Beijing, and then off the edge of the Earth entirely. So you're not going to be able to get unilateral action on a problem where you shift the aim point across the globe and get everybody to say, oh, sure, go ahead. It's going to involve international collaboration and approval. So the Association of Space Explorers back in 2005 started a process of bringing together experts to propose how the UN might decide to deflect an asteroid. And in a nutshell, it involved information, warning, and analysis of asteroid orbits and predicting impacts. A lot of that is already in place at NASA, in Italy, and at ESA, for example, with other interested space agencies cooperating. Then there's the mission planning, or how you plan to deflect an asteroid. The space agencies led by NASA and ESA are just now starting to talk about rules of engagement, about how they can bring their planners together to construct a scenario or a reference mission for a deflection campaign. So that's a good step that they're just getting to this year. And then next year at the UN, we hope to see the committee agree on, the Committee on the Peaceful Uses of Outer Space, based on suggestions from this working group, to come together to talk about approval and oversight of an international deflection campaign. Again, this would be probably led by the space agencies with participation by the members of that committee at the UN who are interested in this problem. And then that would lead to sharing of resources to do a deflection demo led by the space agencies, and then have a book on the shelf to refer to when we actually find an asteroid that's threatening us. So this is exactly analogous to what you do in mission control in Houston or Moscow when there's a problem on the space station. You take down the flight rules that say, problem with the hydraulic system. Refer to the information that we've already worked through here together, and here's the procedure that you execute. You don't have to have a committee convene and start from square zero to do this analysis. You've actually worked through the problem in a general way, and then you can implement a plan that's already on the shelf. And that kind of flight rule approach to advanced planning is the key to responding when we find an asteroid coming towards us. So I'm encouraged. It's just not taken, it's taking more time than I thought it would originally, but I'm encouraged that internationally we can arrive at this decision-making process that endorsed by the UN that will have buy-in from the space agencies who will implement this process, and then we can share resources as well.
Great, thank you. Now, is there another question in the back? Turn the switch on. Let's leave that microphone on.
Can you hear me? Okay. Just two things. One is a comment and question for Tom. This is the comment you mentioned, 2011 AG5. By reassurance, everybody, with about 95% confidence, we'll rule out that impact towards September or October. So don't worry about that one. Other question was for the retrieval mission stuff, which I'd asked you before. How many potential targets do you want us to find? I hope we don't have to find all 500,000 of the objects. Is it okay if we find 10% of them or 1% of them?
Well, I liked your answer in the study, which is Michael proposed that existing ground-based systems, if they're properly focused on finding potential targets for an asteroid retrieval mission, could find about 5 asteroids per year, I think is the number, of the right type, in the right orbit, of the right spin, that this robotic spacecraft, only about 18 tons, could go out and snare an asteroid. So if we have about 5 years to plan the mission, we might have 25 or 30 targets or 20 targets that NASA or its partners could choose from and then send this spacecraft to. And that is the key to making a mission like this feasible, is identifying the targets. So we'd like to see more resources put towards the search for smaller objects using ground-based facilities. And if we can do it from space more efficiently, let's put the resources there. Early implementation of a catalog-filling asteroid search mission is the key to a lot of activities for planetary defense, for human exploration, and for commercial asteroid mining.
And I'd like to invite the other panelists if they have any other closing comments you want to make from this panel. Anything you want to wrap up? You're all looking at each other. David does.
Yeah, I always have something to add. The way we're doing the searches for these asteroids now, and you have to search whether you're worrying about defense or resources or whatever, is the professionals operate the very high-tech telescopes that initially find the objects. And amateur astronomers are doing the follow-up. The amateurs are the ones that measure the position night after night so that we can actually calculate an orbit. And all of this is done with very rapid turnaround. The objects are discovered. By the next afternoon, the data are posted. The amateurs who have the right telescopes and the right ambition and time will go out and follow up. If any of you know any amateurs that are looking for a way to save the world, then they can help with asteroid orbit determination. And I'm sure Peter would say the same thing about the search for meteors and meteorites. We need everybody's help.
I will say in the same kind of story of how can you save the world? Well, you can save the world by making sure that NASA fund big projects that appear to be crazy, but in fact at the end in 20 years will be something we'll be using commonly, like large 30, 40 meter size telescopes I mentioned yesterday. Also this 8-meter class telescope, which is going to be monitoring the sky continuously from Chile on the top of Cerro Pachón. This LSST is, I think, the next big target in astronomy, and it will have a significant impact in monitoring and finding the small asteroid that we will need soon, we will explore soon, but we will also mine.
I really like this fact that 10, 20 years ago, people were only talking about things bigger than a kilometer. 10 years before that, people were not talking about asteroids at all because they were just some leftovers from planets formation. So things have come down, and now it's really exciting to see that there is an interest in 7-meter sized asteroids, because those are the things we could go and bring into the Earth-Moon system and be interesting to study. So now we're talking about really small asteroids. So maybe there's the future. Small asteroids, they're very small, so they don't reflect a lot of sunlight. They're normally faint if they're far away from Earth, but if they're really close, they actually are fairly bright. You could set up surveys for them. Amateurs could do that, looking for plus 14, 15, 16 magnitude objects that are really close to Earth's orbit, and survey the whole sky every night, and really be able to find these and track these, and maybe we get another TC3, something hitting us that we can sample on the ground. So I see a very exciting future here.
Thank you. Any final words, Tom? Okay, that's great. I want to thank you for being here at Asteroids, Junkpiles, or Resources for the Future. And then Pascal Lee, would you stand up for a second? Pascal Lee is going to be at the SETI Institute booth in the exhibit area for the next half an hour, and he'll be available to talk to you about a fantastic opportunity to join his team on Devon Island in the high Arctic. Devon Island is one of the nearest analogs for Mars on Earth. And he's got these great flyers and can tell you all about it. So if you want to be part of his team, go talk to Pascal. Thank you very much, everybody. And thank you, panelists.
And thank you, Edna.
Thank you.
You're welcome. Thank you. You did a great job. Oh, and thank you to our runner with the mic.
I want you to know. Can't wait to read the results.
Wow.